Okay, this is the lesson video for AP Calculus BC for sections 2.5 and 2.6. And what we're going to look at in this video are the derivative rules for trig functions and then also the chain rule. And so this is really the day when we transition from the really basic derivatives into much more complicated derivatives. You'll see once we get to the chain rule, that's where we start to be able to really combine all of the derivative rules and deal with functions that are much more complex from the derivative perspective. So what I wanted to start with here was just a reminder that every one of these derivative rules that we are going to use can actually be proven using the definition of a derivative. And so what I wanted to show you at the beginning is the derivative rule for the sine of x. And the derivative of sine of x is cosine of x. A lot of people already know that, but I wanted to show you why that is the case. So it says on here to use your calculator to confirm these limits. I'm just going to assume that you've looked at that and you know these limits are true. One of them we've already talked about before. Remember we did sine x over x, but it's the same idea. The limit as h approaches 0, sine h over h is 1. And then this second limit we actually looked at on one of the warm-ups where we multiplied by, ours was cosine x, we multiplied by cosine x plus 1. You could do this one that way as well, but you can also just look at it graphically. So the main thing is we have to know the result of those two limits to be able to show that the derivative of sine is cosine. Now I have this here because I wanted you to see on your calculator, you can actually graph derivatives. So if you go in on your calculator and enter sine x as y1, and then on your calculator, if you do math 8 and do the derivative of y1 or the derivative of sine x as y2, then that will show you that you've got the original graph of sine. The second graph that will plot on your calculator will be the cosine graph. Now, keep in mind when the calculator does that, it's not actually graphing the cosine graph, it's graphing an approximation of the cosine graph. So it's a little different than the actual derivative, but it plots it accurately enough that you can see that the derivative of sine is cosine. So what I want to focus on here is this actual proof. So this is the proof that the derivative of sine is cosine. And you can see that we've got the setup using the definition of a derivative here. So dy dx is the limit as h approaches 0 of sine x plus h minus the sine of x divided by h. And what we want to do is figure out a way, how can we actually solve this limit? Because right now, if you plug h as 0 in, you're going to get 0 over 0, which typically indicates for us a removable discontinuity. And when you try to solve that out, the only method we really have is to use our composite properties with our trig functions. And so there's a composite property for the sine function. And you may or may not remember this from pre-calculus, but you can rewrite that sine of x plus h can be rewritten as the sine of x times the cosine of h plus the cosine of x times the sine of h. So you probably did that whenever you took pre-cal. You probably went through that property at one point or another, didn't use it a whole lot, but this is one example where you would use that. I'm not expecting you to know that property. I just wanted you to see this actual proof worked out. So in the denominator here, I still have h. Now, I've still got the same equivalent expression to what I started with. The only thing I did was write it in a different form. And now what I'm going to do is I'm going to group things together in a way that's going to allow me to solve this. So I could rewrite this as the sine of x times the cosine of h minus 1. So what I did was I took the first term here and the last term here, and I factored out a sine of x. Okay, so that's the first thing. And now the second part of this, I still have my cosine x sine h. So that would be plus cosine x sine h. And that's all divided by h. And now what I want to do is group these or rewrite this in a way so that it's obvious that the limits that we talked about at the beginning are going to come into play. So you can see that this is the same as the limit as h approaches 0. And we've got the cosine of h minus 1 divided by h multiplied to the sine of x. And we also have the sine of h divided by h multiplied to the cosine of x. And remember, we're taking the limit as h approaches 0 of all of this. I'm going to use brackets just because I grouped this with some parentheses just to make it clear. So we're taking the limit as h approaches 0 of all of this. And from the limits that we had up above, we know that this one is going to become 1, or this one's going to become 1. And we know that, we know this one's going to be 0. And we know that this one is going to become 1. So essentially we have 0 times sine x plus 1 times cosine x. And in the end, this whole thing just becomes the cosine of x. So what I was talking about with those limits were these two that were at the top. That's what I used in order to simplify that down. So the derivative of sine is indeed the cosine of x. So we could do the same thing. There's the exact same type of setup for the derivative of cosine, and the derivative of cosine is negative sine. I'm not going to go through that, but you can assume that the same methodology would be applied in terms of solving that limit out. Now, once you have those two limits, that allows you, I guess, those two derivative rules that we got using limits. Once we know those two and we have them defined, now we can come up with the other 4 trig derivative rules just by building off the rules we already know. So knowing the rule for sine and knowing the rule for cosine allows me to, for example, get the rule for the derivative of tangent x. Remember, tangent is the same as sine over cosine. So now I can go through, I can take the derivative using my quotient rule and then simplify it down, and I would find that the derivative of tangent is secant squared. Same thing with secant. This is 1 over cosine. I can use my quotient rule, take the derivative, simplify, and you'll see that the derivative of secant is secant x tangent x. Derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant cotangent. So the big takeaway from this is that once we have some of these basic derivative rules defined, that allows us to build new derivative rules. And once we know enough basic rules, we can create as many derivative rules as you want. So we haven't quite gotten there yet where we have all of our basic derivative rules defined, but we have a lot of them. And you can see that these bottom 4 rules that we have here aren't necessarily new rules. They're just applying rules we already know to create kind of a special rule that we can apply for a different function. So within the tangent, we're still using the derivative rule for sine and cosine, but instead of going through that process every time, we're just kind of shortcutting that. So in the end, we've got 6 trig derivative rules. Okay, so let's move on here and start to practice with these a little bit. Now, what I want you to do as you go through this is I want you to notice I've got a bunch of practice problems here. And let's see, it looks like we've got about 10 of them. And then on the next page, there's a little bit of an application for position, velocity, and acceleration. And this is harmonic motion. It's supposed to be a weight on a spring. And so what I want you to do is work through the examples on these next 2 pages. Now, what you'll notice is that we're not just using the basic derivative rules. We're building those derivative rules within other functions, or we're putting those derivative rules within other functions. So now when we take derivatives, we're going to start combining all these rules together. So for example, if you look at this first one, you can see that I'm going to end up using a power rule here, and I'm going to use a derivative of a trig function. You might see product rule, you might see quotient rule, you might see derivatives of the exponentials. In the end, it's still the same process. It's just that the more rules that we have, the more complicated the functions can be that we can deal with. So take a minute, or take a few minutes, pause the video, work through these derivatives, and work through the next page with the simple application. And then when you're done, unpause the video and you can check over your answers. And I've got a couple of things I want to point out on the solutions that you need to be careful about. Okay, so here's what you should have come up with for your solutions. And one thing that I want you to notice is, for example, the first one was very simple. We essentially had 1/2 x to the -1 plus 3 sine x. Just use your power rule, use the derivative of sine. Not really anything special about that. If you wanted to, you could get a common denominator, but really it's fine in that form. But what I do want you to notice is the second one, this one that has the e to the x in the numerator. So in this problem, when you take your derivative and you get to this step, so we've done our quotient rule. That's the only step where we really are using calculus, right? We're going through and we're doing our quotient rule, but then everything after that is just going to be algebra to simplify it down. I want you to get in the habit of simplifying your solutions. And when you simplify them, what you want to be thinking about is that eventually what we're going to want to know about these derivatives, we're going to want to know when is the derivative 0. We're going to want to know when is the derivative undefined. So with that kind of being in the back of your mind, that'll help you decide how do you want to simplify this, because there's a lot of different ways we can write our solution, and not necessarily one is right and one is wrong. What we're trying to do is get in the habit of putting it in a form that's going to be easiest for us moving forward. So eventually we'll have problems where we're going to be looking at a function, its derivative, and the second derivative, and we're going to be analyzing the function off of all of that. And one of the things we have to know is, where's that first derivative 0 or undefined? Another thing we have to know is, where's the second derivative 0 or undefined? So having these in sort of a factored form when possible, especially as it pertains to the numerator, makes it much, much easier. So keep that in mind. Okay, so I'm just going to show you these solutions here. There's not really anything to point out with the x cubed minus 3 secant x, the t cubed cosine t, also very simple. Sine x over x squared. You can see that what I've done here is I've taken, in this form, when I did my quotient rule, notice that I divided out an x. So you really want to be careful about when you divide things out, because remember, we might be eliminating important things about our function. So look at the original function and think about, in this original function, when x was 0, that function was undefined. So really, x equals 0 is a point where we would probably eliminate it from our domain, or we know that the function's not continuous there. So by eliminating that x, when I simplify my derivative down, I'm not losing any critical information. I already knew the function wasn't differentiable at 0. So now with the x gone that we canceled out, I'm still in the same situation where this is the derivative everywhere except where x is 0. Okay, so the 4 secant x plus tangent x, I wrote that in a couple of different forms. Again, thinking about the fact that we want to set that equal to 0, it's probably best to have that in the factored form. The r is equal to, or r of theta is secant theta over 1 plus secant theta. So this one looks really messy at first, but when you go through and you do your factoring and you simplify this whole thing out, it actually simplifies down really nicely. And the big thing to remember on this, when you're taking these derivatives, a lot of times, if you haven't simplified, you're going to look at your answer and you're going to look at, if it's a multiple choice, or you're looking at an answer in the back of the book or whatever it is, your answer might look very different than the final answer when you're at this intermediate step. So make sure you do all of your simplifying before you start trying to compare answers and see if you have the right answer. The sine x over x was very simple. Down here at the bottom, there are a couple of derivatives where we're taking what we call higher order derivatives. So the first problem is asking us to take the 20th derivative of the sine of x. The intent here is not for you to take 20 derivatives. The intent here is for you to recognize that there's a pattern to the derivative of sine. So notice what I did here is I wrote down the first 4 derivatives of sine. So sine, cosine, negative cosine, back to sine again. So it took me 4 derivatives to complete what I would call a cycle of this process. So knowing that to be the case, how many times am I going to complete that cycle? If I go to the 20th derivative, I'm going to complete that cycle 5 times. So I'm going to be exactly at sine x. So you're going to have some problems in your assignment where they're going to ask you to take some really high order derivatives, meaning like they might ask you to take, I don't know, let's say the 87th derivative. I don't want you to try to take 87 derivatives. That's not the point of the problem. The point of the problem is figure out how many cycles you completed, full cycles, and then how many more steps do we have after that, and then you can just figure out where you would be in your process of taking those derivatives with the 4 that you would have to complete a cycle. Okay, so you'll see that behavior with the sine function and the cosine function, but you won't see it with the other 4 trig derivatives. So that's why I showed you the second one. That's why I had you work through this one. You notice with cosecant, if you take the derivative, the first derivative is not bad. Take the second derivative, you can see that this is getting messier. And the more derivatives I take, this is just going to get messier and messier and messier. So we see that secular kind of behavior or circular behavior when we are dealing with sine and cosine, and we are not seeing that behavior with the other 4 trig functions. So, and I think I said secular, I meant circular or cyclical. You can say it either way. Okay, so let's take a look at this one with the harmonic motion. So you'll see some basic application problems in here. Like I've said before, our basic applications right now are going to be position, velocity, acceleration. And that's what we're looking at here. They ask for the position, the velocity, and the acceleration. And pretty easy to do. You're just using your derivative rules. Now on this graph, and my graph got zoomed in a little bit, but on this graph, you can identify which is which. And what I also want you to think about from this graph is when you look at that, notice the relationship between your position function is the solid graph. So when that graph has a 0 slope, notice that the derivative graph, which is this one, it has a value of 0. So that 0 slope matches up with that 0. I could do the same thing with the first derivative graph and the second derivative graph. This one has a 0 slope right around there. Notice the second derivative graph, which is the kind of dotted line here. It's got a 0 value there. So we see that same relationship between the function and the first derivative, and then the first derivative and the second derivative. Okay, and then they say, when's the weight moving the fastest? Well, it's going to move the fastest. Speed is going to be when our velocity is furthest from 0. So it doesn't matter which direction we're moving. So we need to find all those peaks on our velocity graph. And that's going to happen at pi over 2 plus pi n, because we don't really have a domain that we're dealing with here. The slowest is going to be when the velocity is 0, and that occurs at 0 plus pi n. And then it says, how does acceleration compare to position? Pretty simple there. You can see that our acceleration function was -5 cosine t. The position was 5 cosine t. So those are going to be a reflection when you look at the graphs. Okay, so let's take a look at the second part of this, which is the chain rule. And this is really the transition from relatively easy derivatives into derivatives that can start to get kind of messy. And this is where the algebra is really going to pick up in terms of how much you have to do to simplify your derivatives down. So the way the chain rule works is it's sort of a shortcut that we can use in a lot of cases. Sometimes we don't have any choice but to use the chain rule, but I wanted to show you this as kind of a shortcut first. So take a look at this function. Y is equal to 3x squared plus 1. And that quantity is squared. So if I were going to take the derivative of that, I could expand that out and I could take the derivative. It wouldn't be that big of a deal. However, if you think about a binomial that's raised to, let's say, the 10th power, I could expand it out. I could use Pascal's triangle and I could expand it out and I could get the long expression that would represent 3x squared plus 1 to the 10th power. But the reality is that's not very efficient because I can use this chain rule. And I want to show you with a simple example how the chain rule works. And when I say a simple example, we're just going to look at this 3x squared plus 1 squared. So what we're going to do here is sort of treat this as a function that has layers to it. So you treat it as a composite function. So the inside part of this, the 3x squared plus 1, we're going to call that the u. And then we're going to say if that's the case, then y can just be written as u squared. And now notice if I take derivatives here. Here I get dy du because my y is now in terms of u. dy du is 2u. du dx is 6x. Notice that when I took the derivative with respect to x. At that point, remember, I'm looking for dy dx if I'm taking the derivative. So we can actually do some differential math here. So the differentials are just representing small changes in that variable. So if you notice this next step, this is kind of the key to the chain rule. if I were to multiply dy du times du dx, these du's are representing tiny changes in our u. So we can cancel those out, and notice that that gives us dy dx. So what that means is I can go through and I can just multiply dy du times du dx, and that's where this comes from. I don't want my derivative in terms of u. I want my derivative in terms of x. So remember, u was the same as 3x squared plus 1. So now we're going to substitute that back in. And in the end, here's the solution that we come up with when we substitute that in. And if you simplify it down, you get 36x cubed plus 12x. Okay, so remember at the beginning, I said we could expand that one out. So we could have done this way on this one. We could have expanded it out. We could have taken the derivative of that expression. We get the same result. Obviously, in this case, doing the chain rule took us a little bit longer. But if I had an exponent that was a higher order exponent, like let's say it was a 5 or a 6, that would be something where expanding it out is going to be a little bit more work. Taking the derivative is going to take a little bit more time. So typically, we're going to use the chain rule. Now, we don't usually write out all these steps when we do the chain rule. So this is making it look a little bit harder than it is. We really shortcut the majority of this when we do the chain rule. And I'll show you what I mean by that. So if we were to actually work through this the way we did the last one, we would say u is 3x squared plus 5x, and then y is equal to the sine of u. Well, I'm not going to do that. I'm going to jump straight to my derivative here, dy dx. And the way that you can think about this is if I had sine of u, I would take the derivative of sine, it would be cosine. Well, I'm going to have the cosine of that expression, and then I'm going to multiply that by the derivative of the 3x squared plus 5x. That would have been our u. So this is going to get multiplied by 6x plus 5. And that's really my derivative. Now, typically, we would write this in a different order to make it really clear what the 6x plus 5 is multiplying to. 6x plus 5 times the cosine of 3x squared plus 5x. So that would be my derivative. And in that case, I don't have any option in terms of taking the derivative other than using the chain rule. Okay, so we've got different notations we can use. We kind of did this where we looked at y as a function of u. You can say, when we take the derivative of some function of u, it's the derivative of the function of u times the derivative of the inside. So we're essentially doing the derivative from the outside in. And here's an example of that. The derivative of the sine of 6x. Well, take the derivative of the sine, and you get the cosine 6x, and then we're going to multiply by 6. And again, I would typically write this as 6 cosine 6x, because when it's written this way, it's not very clear if the 6 is multiplying to the 6x or the 6 is multiplying to the cosine. All right, so in general, what we're going to do with the chain rule is we're going to work from the outside in. And a lot of times it's described as sort of peeling an onion. An onion has layers to it, and you just unpeel it one layer at a time. And so that's what we're trying to do. So this can be a little bit confusing sometimes, and that's what I want to point out here is be careful with the notation. So this is saying take the derivative with respect to x of the sine of 5x squared. So remember, this is the same as the derivative with respect to x of the sine of 5x, and that whole quantity is being squared. So when I talk about working from the outside in, make sure you're going through the correct process there. So the derivative of the sine of 5x squared, I'm going to start with the exponent. So it's 2 sine 5x times the derivative of the sine, which would be cosine 5x, times the derivative of the 5x, so times 5. So in the end, what I'm going to end up with here is 10 times the sine of 5x times the cosine of 5x. And if you wanted to, you could use trig identities. You could simplify that down, but the main idea there is taking the derivative. Okay, so this is the first form of the chain rule that we looked at with the differentials. It says the same thing as the other form that we had. Okay, so we've got a bunch of examples here that I want you to try. And kind of the same thing as before. I want you to work through these examples, and then I'm going to show you the solutions so you can check over your answers. So pause the video, work through all the problems, and then you can unpause the video when you're done. Okay, so here's the first two questions, and there's not really a lot of simplifying to do here, but you can see that these are examples of ones that if we really wanted to, we could expand them out first and then take the derivative, but it makes a lot more sense to work them in this order, just use the chain rule. All right, on the next page here, you start to see some of the algebra that happens with these. For this first one, square root of 5 minus t, the easy thing to forget about this, when you do your chain rule, notice I wrote it as 5 minus t to the 1/2 power. Don't forget, after you do your power rule, that's the derivative of the inside. The derivative of the 5 minus t is -1. Okay, on the second one, we've got x over square root of x squared plus 1. So again, we're going to use quotient rule, but within the quotient rule, we've got the chain rule. So when you do the quotient rule here, you can see in this intermediate step, we kind of have a mess here. And really, that would be a complex fraction if I wrote it all out. So I did some algebra, and I didn't show all the steps, but you'd have to do some algebra to get from the derivative step to our simplified form. And you can see that that looks like a big mess at the beginning. And then my answer is actually a pretty nice form. So again, if you were doing like a multiple choice question, you might do that first step and look at the answer choices and think, well, there's no way that I've done this right because this is a mess. But the reality is, a lot of times on these, you're going to have to do a pretty substantial amount of algebra to get them simplified down. Okay, so here's another example of one where you've got to do a little bit of factoring. In this case, a little bit of algebra to simplify it. So I did my product rule. Within the product rule, there's chain rule. And then once I did my chain rule, I did factoring by grouping and got it into a simplified form. This one, 5 tangent 3x, is pretty straightforward. Just remember, after you take the derivative of tangent, don't forget to take the derivative of the 3x. So this one says cosine 1 minus 2x squared. So remember, I put this one in here intentionally for the notation. If that 2 was written here instead, that would be the cosine being squared. But with the 2 being applied to the argument, that means the 1 minus 2x is squared. So you could expand out that 1 minus 2x if you wanted, but I went ahead and did my chain rule here. And notice when I took the derivative of the 1 minus 2x squared, that's where I did the chain rule. Okay, so on the next one here, sine squared 8 theta. When it doesn't say what to take the derivative with respect to, you can assume you're taking the derivative with respect to whatever variable you're dependent on. So in this case, we're taking the derivative with respect to theta. Pretty simple one. You can see I wrote the answer in 2 different forms. Here we've got square root of x plus 1/4 sine squared 2x. This is another one where now the 2 is applying to the sine. So the sine's being squared, not the 2x. So pretty simple on that one. Next one here, this one's got a few layers to it. So you can see that the 3, the exponent of a 3 is what I deal with first. Then I'm just working my way from the outside in to get to my final solution. And once you get there, there's not really a lot of simplifying you can do. This one's asking for a second derivative of tangent 5x. Pretty straightforward. This one asks for the slope of the tangent to the curve. And a lot of times on these, you're going to have options. So make sure you account for which method is going to work best for you when you're taking your derivative. So when I'm looking at this function, I could do that with the quotient rule. For me, I don't like all the algebra that's involved in the quotient rule. So I usually rewrite the function in a way that is going to minimize how much quotient rule I have to do. And that's why I started with this step, because I wanted my function in an easier form for me so I didn't have to do quotient rule. You'll get the same answer for the derivative either way. It's really just a matter of preference. And now that you know the chain rule, you're going to have a lot of problems like that where you can kind of, pick which way you want to go about solving the problem. Any quotient rule question can be turned into a product rule question. Any product rule question can be turned into a quotient rule question. So it's really a matter of convenience when you're trying to decide which way to do them. And then these last problems, these are written in a more general form. So the idea on these problems is to make sure you understand what the general derivative rule is. And the first one is just basic product rule, so I won't really go through that one, but take a look at this one. G of h of x. Notice my derivative would be g prime of h of x times h prime of x. So you still have to do the derivative of the outside times the derivative of the inside. So don't forget about that when you work through those. And you can see the solutions for all of those in that general function notation. This is a really common type of question that you're likely to see on your homework, on your quiz, on the AP test at the end of the year, because it's a really easy way that you can tell if somebody really conceptually understands the derivative rules. Okay, so that's everything in those two sections. The big thing here, make sure you have those 6 trig derivative rules memorized. The nice thing is you can always figure out the 4 that aren't sine or cosine. You can figure out tangent, cotangent, secant, cosecant pretty easily if you forget them, but you have to know sine and cosine. And then practice a lot with the chain rule, because it's not so much the derivatives on the chain rule, it's going to be the algebra that you have to do to simplify after you've done the chain rule. So if you have questions on this, make sure you ask me next time in class. And if anything comes up on the Wiley Plus, you know, put a star next to it or somehow write that down so that when we have time in class to go through problems, you can bring that up and we can go through those problems.